In my previous video, I have seen some test of subgroup test, cyclic subgroup, order of element of a group and cyclic group. Let's recall again this property. At first recall order of element of the group. Let A be an arbitrary element of a group. If the cyclic subgroup generated by A is finite, then the order of A is the order of the cyclic subgroup generated by A. And if the cyclic subgroup generated by A is infinite, then we say A is of infinite order. Let's see some example. What is the order of the element 1 in Z4? I have told how many elements contain the cyclic subgroup generated by A is the order of this element. Here, look, cyclic subgroup generated by 1 is 1, 1 plus 1 equal to 2, 1 plus 1 plus 1 equal to 3, and 1 plus 1 plus 1 plus 1 equal to 4, which is congruent to 0 in modulo 4. This is the cyclic subgroup generated by 1, and this contains 4 elements 0, 1, 2, 3, which is equal to 4. Therefore, order of the element 1 in Z4 is 4. Now my question, what is the order of 5 in Z? The element 5 is of infinite order. Since the cyclic subgroup generated by 5 equal to 5Z, which is of infinite order, that means which contains infinite number of elements, cyclic subgroup generated by 5. So, order of 5 in Z is infinite. Are you getting my point? Well, if the cyclic subgroup generated by A is finite, that means cyclic subgroup generated by A contains A squared, e to the power n minus 1 and e to the power n, which is equal to E. This is the cyclic subgroup generated by A. A squared up to e to the power n minus 1. Here E is nothing, E is e to the power n, and e to the power n here equal to E. That means cyclic subgroup generated by A contains n elements, where n is the least positive integer such that e to the power n equal to E. Are you getting my point? So, there are alternative definition, order of an element of a group. What is the definition? Let A be an element of a group G. Then order of A is the least positive integer such that e to the power n equal to E. And if no such integer exists, then A is said to be infinite order. Are you getting? What is the order of element of a group? I have discussed in my previous video what is the cyclic group. Now just recall what is the cyclic group. G is called cyclic group if there is an element A in G such that cyclic subgroup generated by A equal to group itself. Then the group is called cyclic group, and which I have discussed elaborately in my previous video. Let's see one important example of cyclic group. Prove that set of all nth root of unity from a cyclic group with respect to multiplication. Okay, that means let Un be the multiplicative group of nth root of unity in C. Then Un consists of the number given by cos 2 pi r over n plus I sin 2 pi over n, where r equal to 0, 1, 2 up to n minus 1. Let's consider n equal to 3. Then u3 contains the equation x cube minus 1 equal to 0. That means u3 contains the element 1 minus 1 plus I root 3 over 2 minus 1 minus I root 3 over 2. Okay, u3 contains this element. Similarly, let's consider n equal to 4. Then u4 contains the equation x to the power 4 minus 1 equal to 0. That means u4 contains the element 1 minus 1 I minus I. Similarly, if I generalize the equation, then I will get x equal to 1 to the power 1 over n. That implies x to the power n equal to 1. Then all of us know 1 equal to cos 0 plus I sin 0, which we can write cos 2 pi plus I sin 2 pi, and this is equal to, similarly, because we all of us know cos 2 pi equal to 1, cos 4 pi equal to 1. Similarly, I can get cos 2 pi r plus I sin 2 pi r. Then 1 to the power 1 over n equal to cos 2 pi r plus I sin 2 pi r to the power 1 over n. And we all of us know Euler's theorem. Cos theta plus I sin theta to the power n equal to cos n theta plus I sin n theta. Therefore, by Euler's theorem, we can write it cos 2 pi r over n plus I sin 2 pi r over n, where r equal to 0, 1, 2 up to n minus 1. Okay? And we also know e to the power I theta equal to cos theta plus I sin theta. So, cos 2 pi r over n plus I sin 2 pi r over n equal to e to the power 2 pi r over n, which I can write e to the power 2 pi over n to the power r, where r equal to 0, 1, 2 up to n minus 1. Okay? Well, let's consider e to the power 2 pi I over n equal to omega. Then G contains the element 1 omega, omega square up to omega to the power n minus 1. That means integral power of e to the power 2 pi over n can generate whole the group G. That means e to the power 2 pi I over n is the generator of the group Un. So, Un is a cyclic group. Are you getting my point? Well, lot of mathematicians think about multiplying matrices. They found out multiply matrices with one way and multiply same matrices in another way. You usually don't get the same answer. And the moment is a big moment. R, Q, C, Z are all commutative group. But matrices are not commutative group. So, in abstract algebra, we want to do a question. What kind of algebra will satisfy this property? This is commutative property, which is special case of the group. Most groups don't have this property. When whole group satisfy this property, then we can call it abelian group. Okay? And today I want to focus those groups which are not abelian, but focus on the place which satisfy the commutative property. This is the center of a group. Let's see the first definition. Given a group G, the center of group G is, who is defined as ZG. ZG is denoted as center of a group. Set of all G such that Gx equal to Xg for all X belongs to Z. That means all elements of the group that commute with other element of the group. Okay? Are you getting what is the center of a group? Well, actually, center of a group is a subset. And this subset always will be non-empty. Because every group has at least one element, which is identity element. And identity element commute every element of the group. That means center of a group always contain identity element. And it may also have other thing. If the group is abelian, then every element commute with every element of the group. And when the group is abelian, then center of a group will be the whole group Z. But when the group is not abelian, then it will be just a subset. Okay? That means what is the center of a group? If G be the member of the center of a group, then it commutes other element of the group. That means Gx equal to Xg for all X belongs to Z. That implies Gx G inverse be the member of the ZG for all X belongs to Z. Okay? And this is the equivalent condition of this line. Are you getting my point? Well, there is a theorem. The statement of the theorem is the center of a group always will be subgroup of G. And I will prove this theorem by one-step subgroup test. And this step I did in my previous video elaborately. Just see the statement of this test. Let S be any subset of the group G, and for all xy be the member of S, then xy inverse must be the member of S if S is a subgroup of G. Okay? That means at first we have to consider any subset. We all of us know ZG is a subset of the group G. Let's consider any two member X and Y of ZG. Then by definition, we all of us know Gx G inverse equal to X for all G belongs to Z. Similarly, Y equal to Gy inverse Gy Z inverse where for all G belongs to capital G. Now consider xy inverse. What is x? X equal to Gx G inverse. And what is y? Y equal to Gy G inverse. Then this is x, put the value x and put the value y. And this here y inverse. We have to prove x y inverse must be member of the ZG. Then it will be subgroup. By inverse property, we all of us know AB inverse equal to B inverse, A inverse. So this will be by this property similar to, and we all of us know J inverse J equal to identity. So this will be identity. That means it will be Gx Y inverse G inverse, and this is similar to G times X Y inverse times G inverse. And from this line we can write easily XY inverse G equal to G times XY inverse. That means by definition of the center of a group, XY inverse must be member of the center of a group. And our proof has done because XY inverse be the member of the group, center, member of the subset center of a group, where X and Y be the member of the subset center of a group. So, center of a group always be the subgroup of the G. Okay? Well, now let's see the nice non-abelian group of order 8. This is Quatrainian group. And this set contains plus minus 1, plus minus I, plus minus j, plus minus k. That means this set contains 8 elements, and this is denoted as Q8. At first I will see the subgroup of this Q8. Then I will see what is the center of this group of this element. Okay? Here minus 1 square equal to 1. So 1 is the identity element. And I square similar to j square similar to k square, which is equal to minus 1. Here I times j equal to k, j times k equal to I, k times I equal to j. This follows this picture. When I go clockwise, then it will be I times j equal to k, j times k equal to I, k times I equal to j. But when I will follow same picture with anti-clockwise direction, then it will be j times I equal to minus k, k times j equal to minus I times k equal to minus j. And here I to the power 4 equal to 1, so order of I equal to 4, j to the power 4 equal to 1, so order of j equal to 4. Similarly, k to the power 4 equal to 1, so order of k equal to here 4, and this is the structure of the group Q8. Okay? Are you getting? Well, now let's see the subgroup of Quatrainian group. We all of us know cyclic subgroup generated by A equal to e to the power n, where n belongs to integer. Consider S1 equal to cyclic subgroup generated by 1, and this will contain only one element, because 1 to the power any power always will be 1. That means this cyclic subgroup contains only one element, and order of this cyclic subgroup is 1. Other subgroup is cyclic subgroup generated by minus 1, which contains the element 1 and minus 1. Because we all of us know minus 1 to the power 0 equal to 1 and minus 1 to the power 1 equal to minus 1. And minus 1 is square equal to 1, which will back to the element 1. That means the cyclic subgroup generated by -1 contains only the elements 1 and -1. So order of this subgroup 2. Other subgroup, cyclic subgroup generated by I. We all of us know I to the power 0 equal to 1, I to the power 1 equal to I square equal to -1 and I cube equal to -I. And I to the power 4 equal to 1, which will get back to the identity element. So, this cyclic subgroup only contains these 4 elements. So, H3 has order 4. Similarly, H4, the cyclic subgroup generated by J, which contains the elements 1, J minus 1 minus J. This contains only 4 elements. So, the order of the cyclic subgroup generated by J is 4. Similarly, other cyclic subgroup of order 4 is the cyclic subgroup generated by K, and this set also contains 1 minus 1 minus K. Notice the cyclic subgroup generated by -I equal to -I to the power 0 equal to 1, -I to the power 1 equal to -I, minus I square equal to -1 and -I to the power cube equal to I. And after this, other element will come back in this element. So, minus cyclic subgroup generated by -I contains only those elements which is similar to I. That means the cyclic subgroup generated by I and the cyclic subgroup generated by -I is similar subgroup. Similarly, if you notice -J, the cyclic subgroup generated by -J, who is also similar to the cyclic subgroup generated by J. Similarly, K, the cyclic subgroup generated by K, similar to the cyclic subgroup generated by -K. That means this set only 6 subgroups. H1, the cyclic subgroup generated by 1, H2, the cyclic subgroup generated by -1, H3, the cyclic subgroup generated by I, H4, the cyclic subgroup generated by J, and H5, cyclic subgroup generated by K, and H6 is group itself, means Q8. Are you getting what is the subgroup? Okay. Now, let's see the diagram of this subgroup. This is the group itself, and there are 3 distinct cyclic subgroup of order 4. This is cyclic subgroup generated by I, cyclic subgroup generated by J, cyclic subgroup generated by K. Okay? And these 3 cyclic subgroup contains the cyclic subgroup generated by 1, which has 2 elements. That means this cyclic subgroup is of order 2. And this also contains the cyclic subgroup generated by 1. Okay? Are you getting this diagram? Well. Now, let's see a new subset G, which is equal to the set containing 2 cross 2 matrices 1 0 0 1, -1 0 0 -1, I0 0 minus I 0 I 0 1 minus 1 0 0 minus 1 1 0 0 I 0 and 0 minus I 0. And this set is nothing. This set is just GL2C, because we all of us know what is the group GL2R. GL2R means set of all matrices with non-zero, set of all 2 cross 2 matrices with non-zero determinant. Here C, because here the element complex. So this set be the member of GL2C group. Okay, and this is similar Q8, because Q8 contains the element 1 minus 1, I minus I, j minus j, k minus k. Here 1 is equivalent to the matrices 1 0 0 1, minus 1 is equivalent to minus 1 0 0 minus 1. Okay, similarly I is equivalent to I 0 0 minus I, and minus I is equivalent to minus I 0 0 I. Similarly, j is equivalent to 0 1 minus 1 0, and minus j is equivalent to 0 minus 1 1 0, and k is equivalent to the matrices 0 I 0, and minus k is equivalent to 0 minus I 0. Now you can ask me why you have considered I equal to these matrices? Because if we consider these matrices, then the operation will be same, because here the operation I square equal to minus 1. If we consider these matrices, now check I square, this is equal to minus 1 0 0 minus 1. Okay, and this is same as these matrices, and I have considered these matrices is equivalent to minus 1. That means this is equivalent to minus 1. That means I have got I square equal to minus 1. That means this operation has satisfied here. Similarly, if I consider j equal to these matrices, then after this operation I will get z square equal to these matrices, which is similarly equal to these matrices, which is equivalent to minus 1. So j also satisfies this operation. Similarly k. So our assumption is right. Here I times j equal to k. If we multiply those matrices, then I will get this, and this is similar to k. That means it is also satisfied. So this set satisfies all operation of Q8. So what is conclusion? Q8 and this set is similar. So those subset which will satisfy this operation, this subset will be same, the group Q8. Are you getting? Okay. And this group Q8 is not abelian, because I times j equal to k, and but j times I equal to minus k. That means element here does not commute. So Q8 is not an abelian group. Okay. Now my question, what is the center of the group Q8? I have considered this group because this group is not abelian. 1 belongs to ZQ8, Because we all of us know 1 always commute every other element of the group. So 1 always be the member of ZQ8. Similarly, -1 be the member of ZQ8 because -1 times x be any member of the group Q8 equal to x times -1 which is equal to -x. So 1 and -1 both be the member of ZQ8. Now my question, is I be the member of ZQ8? Notice I times j equal to k and j times I equal to minus k. That means I does not commute to any element of the group Q8. So I does not be the member of ZQ8. Similarly, j does not be the member of Q8. Also, k does not be the member of ZQ8. That means ZQ8 only contain the elements 1 and -1. Okay? Well, there is a nice theorem. Every cyclic group is abelian. Let's see the proof. Suppose G is cyclic group. That means G is generated by a singleton element X. Now, take any arbitrary member of the group G. Let A consider A be member of G. Then, since G is a cyclic group, then we can write A equal to x to the power n and B equal to x to the power m for some nm belongs to integer. And we need to show AB equal to BA. AB equal to x to the power n times x to the power n, which is equal to x to the power n plus m. And we all of us know addition is commutative operation in the set of integer. So this and this are same. It equal to x to the power m times x to the power n, and x to the power m equal to b and x to the power n equal to a. That means AB equal to BA. So G is a abelian group. Okay? Alright. But every abelian group may or may not be cyclic. Look, this group are under addition. This is abelian but not cyclic. And I have proved in my previous video Q is not cyclic group, but Q is an abelian group. Similarly, complex number under addition. But Z under addition is both abelian and cyclic group. So, abelian group may or may not be cyclic. Okay? And since Q8 is non-abelian, so that imply Q8 is non-cyclic. Okay? That means this is the example of order 8 group which is non-cyclic. Now the interesting thing of Q8, all proper subgroup of Q8 is cyclic, but the group itself means Q8 is not a cyclic group. And this is the example of the group which is non-cyclic, but every proper subgroup is cyclic. And this is very important example for any comparative exam. Okay? Well.